we are going to talk about one of the most basic effects in the theory of relativity, and how it completely changes the way we think about time. Are you ready? Let's jump right in. So what is special theory of relativity? As the name suggests, it focuses on the things that are relative. And this is something that I already kind of know from the class. Most speeds are relative, meaning they depend on where you compare them to, like your reference rate. If you're standing on the side of the highway and the Lamborghini just blasts past you, you'll be like, wow, that was fast. But if you are in a rocket ship that's moving way faster, and you look down at the same highway, the Lamborghini might actually look slow. It is the same car, but totally different point of view. So normally, speed depends on the observer. Now, here's where Einstein steps in and changes everything. He proposed that light is special. No matter how fast you move, you always measure the same speed of light. It is about 3 times 10 to the 8 meters per second. It doesn't matter if you're standing still or flying in a rocket ship in the opposite direction. You still get the same number. No matter how you move, the speed of light stays the same. That makes it the ultimate speed limit of the universe. This idea comes from Einstein's second postulate, which says that the speed of light in a vacuum is the same for all observers, in all inertial reference frames, which is basically saying as long as we're not talking about acceleration. Now, let's do a thought experiment. Imagine you're inside a fast-moving train with 2 mirrors, like one on the floor and one on the ceiling, and a tiny beam of light bouncing straight up and down between them, kind of like a basketball going up and down. So from the inside of the train, like everything looks simple, like the light just goes straight up and straight down, repeat. Nothing weird so far. But if you're standing outside, things look very different. So the light doesn't look like it's going straight up and down anymore. Instead, it follows a diagonal path. And that diagonal path is longer. So here is the key. Speed is distance divided by time, and everybody knows that. And the speed here is c, the speed of light. Since everyone has to measure the same speed of light, as we mentioned before, if the outside observer sees the light travel a longer distance during the same bounce, the only way for the formula to still work is for the time to be longer. Wait, so the outside observer concludes that the clock on the moving train ticks more slowly? Time stretches, and that effect is called time dilation. Now, how much does time actually stretch? Because this situation forms a right triangle, we can use the Pythagoras theorem to relate the distances. When we plug in the speed of light, simplify the math, and divide by the clock's normal time, we end up with a single number that tells us exactly how much time stretches. This number is called the Lorentz factor, written as gamma. Think about gamma as a time stretch multiplier. And this graph shows what gamma really does. On the x-axis, we have speed as a fraction of the speed of light. You can think of it like a percentage, like 0.1 means like 10% speed of light, 0.5 means 50%, 0.9 means 90%, and so on. On the y-axis, we have time dilation. The Lorentz factor gamma. If gamma is 1, time is normal. If gamma is bigger than 1, time runs slower for the moving object. At low speeds, you can see the graph is almost flat, so the time dilation is basically unnoticeable in everyday life, which makes so much sense. But as you get closer and closer to the speed of light, the curve suddenly shoots upward. Gamma increases really fast and keeps growing as you approach light speed. That means time dilation becomes huge. So here's a question for you real quick. If you're traveling in a spaceship like in 99.9% the speed of light, how much time would you pass on Earth? If something takes you 10 years. The answer is about 224 years. You only age 10 years, but more than 2 centuries passed on Earth. Well, that's basically going to the future. So today, we learned Einstein's big idea about light, time dilation, and the Lorentz factor, which tells us how much time stretches and when you move close to the speed of light. So next time, we'll talk about other effects of special relativity and whether they're important for understanding of gravity. See you next time. Bye!
Free audio post-production by alphonic.com